Hello, everyone. I'm Norman Wahlberger. Thanks for joining me on this adventure towards understanding algebraic calculus via de Castelnau-Bézier curves. Today, a really big step up as we move from the quadratic situation, which we've been studying quite a lot, to the much more complicated, really, version of cubic curves. And so the world of cubics in algebraic geometry and number theory is a very rich subject, with the elliptic curves, or sometimes called non-singular cubics, sort of playing a central role in the modern theory. And that's intimately connected with cryptography, with modern powerful forms of cryptography, and also with mathematical physics and string theory, and also with number theory, like the Fermat-Last theorem and the famous conjectures. But it's rather a difficult or imposing subject for amateurs to get into. One of the reasons is that the elliptic curves themselves are a little bit say hard to get at, hard to access directly, because, well, the usual treatment relies very much on a complex number or real number framework. And so from our computational, feet on the ground point of view, it's harder to pin down what's really going on there. So as a kind of a stepping stone to that very rich theory, I want to talk about, naturally, de Castelnau-Bézier curves. These polynomially parameterizable curves, which are, of course, much more accessible, but still, it turns out, very rich. And some of the phenomena, in fact, a lot of the phenomena for the elliptic curve story already appears in this much more elementary, hands-on, accessible framework. So I think this is a great place to start in moving in this direction of analytic geometry / modern algebraic geometry. We'll also, during the course events, find out that aspects of differential geometry can also be addressed with these examples foremost in mind. That there's a strong differential geometrical aspect to these things, so notions of curvature and Frenet formulas and Frenet frames. These things can be discussed in the context of these de Castelnau-Bézier curves. So these can be studied in the context of DCB cubics and more general curves also, of course. Now, our starting point is going to be this, I think, novel theorem, which I really love this theorem. I think this is a great sort of carrying on directly from Archimedes' original insight into the parabolic situation. So I'm claiming that Archimedes' parabolic area formula actually has a direct analog, a direct extension to cubic de Castelnau-Bézier curves. But there's an important sort of condition. They have to be a certain type of de Castelnau-Bézier cubic. And this type is pretty interesting. So it's a sort of a subfamily inside the world of cubics, which has some remarkable properties. We're going to meet a lot of them today. So it's a bit of an overview today. We're not going to get into proofs, but I just want to explain what's going on. So here is the main theorem that we're interested in. If gamma is one of these Archimedean DCB cubics, which I'll tell you what those are shortly, with control points P0, P1, P2, and P3. So there's P0, there's P1, there's P2, and there's P3. And Archimedean point C, okay? So this is some special point on this DCB cubic. Then the region R formed by the curve, gamma, so this curve here going from P0 to P3, and then back again along the line P0, P3. So this region in here, okay? This has a signed area which is definable and computable, and remarkably is 4/3 the signed area of this inscribed triangle, P0, C, P3. So this is almost verbatim the same as the parabola area formula of Archimedes. In particular, that constant 4/3 is appearing here. So let's have a look at this diagram. Let me explain what's going on here. So I've already said we've got these 4 control points, and here are the Q points. So Q0 along the way between P0 and P1, and here's Q1 along here, and Q2 along here. This particular snapshot shows the value when T is equal to 0.7. Okay, and then correspondingly along Q0, Q1, we have the point R0, 0.7 of the way along, and between Q1 and Q2, we have R1, which is 0.7 of the way along. And then between R0 and R1, 0.7 of the way along is this point S0. And this S0 is what traces out this DCB cubic. Okay, so that's the meaning of those things. Now I have to tell you, what is this point C? So in the parabola story, the point C was characterized by a number of different ways. Okay, one was that this was the unique point that gave a maximal inscribed area of this triangle here. Okay, another one was that the tangent here, which is in pink, was parallel to the base from P0 to P3. And then there was also a midpoint condition between this vertex here and the midpoint of the base. So this point C had a number of different characterizations. So which one of those characterizations is maybe the most fundamental becomes clearer when we extend our story and try to see this in a bigger picture. Here, you can see, I'm sure, that this tangent is in fact not parallel to the base. So that criterion is out. It turns out, therefore, that implies that also this inscribed area here of this triangle is not the maximal inscribed area. Okay, it's not. So those characterizations of the point C are not what's involved. So how do we characterize this point C? Well, it's also obtainable in a kind of a midpoint fashion. But what you need to do is you need to look at the midpoint of the base, P0, P3, and also the midpoint of the top from P1 to P2. So there's the point L there and the point M there. And if you take the midpoint of L and M, you get this point N. Okay, and then if you take the midpoint of N and L, you do indeed get the point C. So that's the definition of this point C, or one definition of it. And now let's just check here on this GeoGebra slide what's actually involved. So if you look over here, poly 1 equals 2.42. That's GeoGebra's estimate of the area enclosed here that we're interested in, the actual slice of the cubic by this chord P0, P3. And this triangle here, that's T1, that's 1.817. And this very bottom line here that you see is something like U sub 1 or something equals 1.333. That is the ratio of poly 1 and T1. It's the factor that relates the cubic arc area and the triangular area. And it's 1.33. Which is the incarnation of 4/3 that we're seeing here. So this is a verification, at least in this particular example, of this remarkable Archimedes formula, which we now see has an extension to the cubic case. And in my opinion, this is beautiful enough that it should be in every calculus textbook. Undergraduates should learn both the parabolic version of Archimedes and this cubic version, which I'm showing you now. But to really understand this, I have to tell you, what is an Archimedean DCB cubic? Okay, so here is the definition. A DCB cubic gamma with control points P0, P1, P2, and P3 is Archimedean. So we're making a definition. Precisely when there are 4 equally spaced parallel lines through the control points. 4 equally spaced lines, parallel lines through the control points. In this case, these lines are this line here, which is the line x equals 0. Okay, you don't see the coordinates, but that's how it was this is x equals 1 through P1, x equals 2 through P2, and x equals 3 through P3. These lines are indeed parallel, and the 4 control points sit on those 4 parallel lines. Now, this really is a condition. If you take 4 general points in the plane, they will not satisfy this condition generally. However, 3 points always will. I want you to convince yourself of that. It's a pretty easy kind of argument. If we just look at P0, P1, and P3, and there are any 3 points which are, let's say, non-collinear, then we can always find 3 parallel lines through those which are equally spaced. And that's a purely affine notion. So this property of the 4th point also lying on one of these equally spaced 4 parallel lines is a legitimate condition on the control points. And the control points, the general set of control points is not going to satisfy that. So that's the definition of an Archimedean cubic, or at least one relatively simple definition that's easy for me to state. And now I need to tell you what this point C is. Okay, well, I've told it to you in terms of being the midpoint of L and N itself was the midpoint of M and L, and these L's, M's were midpoints of the various control points. So another way of saying that, maybe in an affine fashion, is that you can think of C as being this affine combination. It's a combination of these 4 control points with coefficients 1/8, 3/8, 3/8, and 1/8. And this shouldn't be too unfamiliar, because what we really have here are the binomial coefficients 1, 3, 3, 1. We're just dividing by the total, 8. Okay, so this is sort of the binomial weightings appearing here. So basically, we're putting weights of 1 on P0 and P3, weights of 3 on P1 and P2, and then this point will be the point of balance of this mass distribution. Okay, so that's, by definition, the Archimedean point of the DCB polygon. The polygon is P0, P1, P2, P3, and this, we'll say, is the Archimedean point of the polygon, and that's what appears in Archimedes' area formula in this case. That's how you get the inscribed triangle area that you have to multiply by 4/3 by to get the highly non-trivial cubic sector area. Now, I'm going to tell you a little bit more about this because it's very interesting. So let's have a look at this next one. This next one is an alternate way of understanding this Archimedean property. So the DCB cubic gamma that we're looking at with control points P0, P1, P2, and P3, the claim is that this is Archimedean precisely when this relationship holds between the signed areas of the DCB polygon, P0, P1, P2, P3, and a variant of it, the sort of twisted polygon, P0, P2, P1, P3. There's a factor of 2 here. So let me show you that in this case here. So here's a similar kind of picture, and over here in Q1 in green here, this value of 3.288 refers to the polygon area, the whole polygon, P0, P1, P2, P3. That big polygon has area 3.288. Okay. Now Q2 down here is referring to this sort of signed area. So we start at P0, then we go up to P2, and then we go over to P1, and then we go down to P3, and we come back to P0. So that has the effect of essentially utilizing these 2 sort of subtriangles. This one here with an orientation this way, and this one here with an orientation in the opposite direction. Because as we walk along the boundary here that I'm talking about, okay, we're walking all the way along here. We're going around this triangle in this direction, but we're going around this triangle in this direction. And in the algebraic calculus, area is almost always a signed area. So the orientation is crucial. Otherwise, you don't have the proper additivity and things don't fit together properly. Okay, so when we're talking about the signed area of this polygon here, we have to take the signed area of this thing here and essentially sort of subtract the signed area if we were going in the same direction. Okay, and so that's the cumulative effect of that, and GeoGebra can figure that out. So GeoGebra knows that when we do a zigzag like this, it has to sort of weight this area negatively for a total of 1.644. And you can see indeed that 3.288 is indeed 2 times 1.644. And I'm saying this is the manifestation of the Archimedean property. So if you had just 4 points in the plane, I'm claiming that instead of trying to figure out whether there were 4 equally spaced parallel lines through these 4 points, you could just compute these 2 signed areas of these polygons. And if one of them was twice the other, you would know that this is an Archimedean situation and that the corresponding DCB curve is Archimedean in the sense I've defined. Now, there's another characterization of this, which is this statement here. And there's a lot to say about this, but I'm just going to introduce you to this idea. Okay, so this is another condition that captures this Archimedean property. So this Archimedean property, I think, is very important. Okay, so here's another characterization of it that really sheds more light. It's sort of a big picture, point of view. So this Archimedean property occurs precisely when the unique point at infinity on the curve is singular. Okay, now to properly make sense of that, I have to talk about the point at infinity. And I remember when I was talking about the parabola, I also said that we would ultimately have to talk about the point at infinity because the parabola is tangent to the line at infinity in a projective setting or projective sense. Here, this curve goes through the point of infinity. Basically, what that means is that you follow the curve, and as the parameter t gets either very big or very small, and you follow it, and it's sort of heading out in a certain direction. Okay, it's not changing direction. It's going more and more in one direction as it gets bigger, and then that's one way of thinking about the point at infinity is the direction that it's going in. Or if you also look in the other direction, you get the same point at infinity. The 2 directions are essentially the same. That's how projective geometry works. Okay, so there's something to explain there. We need to understand a little bit about projective geometry. But the key point is that there's actually a projective point at infinity, on the line at infinity on this curve. Okay, and this is a crucial insight of algebraic geometers for hundreds of years, that these points at infinity have a lot to do with the curve. And this is a beautiful case in point. Okay, so what does it mean to be singular? Well, for a cubic, singularities are basically where you don't have a well-defined tangent. So here you have a well-defined tangent. Okay, but that well-defined tangent doesn't always exist. So if the curve has a node, in other words, it sort of loops around, like it goes like this, okay, like so it crosses, okay, then it's not going to have a well-defined tangent at that point because that could be a tangent, that could be a tangent, sort of 2 tangents. And another kind of situation is where you have a cusp, where you have sort of 2 things coming in like this, and there's a kind of a double tangent in some sense. So it's not a proper tangent. So those are singular points. And if the point at infinity is singular, that's a characterization of these Archimedean cubics. Now, this is very pleasant because it's kind of freeing oneself from the actual 4 control points that we have on the page. This is just a property of the curve at large. There's a point at infinity, and the nature of that determines what's going to happen here. So that's allowing us to deduce the also very interesting fact that if one set of DCB control points has this Archimedean property, like say this one here that I'm showing you, then all sets of DCB control points will have that property. If we subdivide the curve, perhaps several times, and you get another 4 control points for some piece of the curve. Then those 4 points will also have this property that you can find 4 parallel lines through them, which are equally spaced. So, yes, this property of these Archimedean things is very interesting. And so also, while I have this thing here, I also want to, I've been talking about this tangent here. This tangent is pretty interesting. Oh, maybe my next theorem talks about that. Let's have a look. Oh, yes. Okay, yes. So here's the next point is what happens at the tangent at C. This is also pretty interesting. Let me remind you that in the parabolic case, the tangent at that maximal point was parallel to the base. Okay, and it was, remember, there was a sort of a construction of it. We had various constructions involving this base point and then sort of going, parallel for the base point. So here, the tangent at this Archimedean point C passes through the meet K, this point K, which is just the meet of the 2 lines, P0, P2, and P1, P3. So that's enough to construct the tangent to this curve if we already know what the point C is. How about if we don't have the point C and we want to say still construct this tangent? So the next statement is that it also passes through E. What is this point E? E is the midpoint of the segment from P1 to this point down here. And what is this point? This point is the midpoint of the segment from P0 to P2. So we take the mid-segment, midpoint of that, and then we take the midpoint of that, we get this point E. And similarly on the other side, if you take the midpoint of P1, P3, you get that point there, and then you take a further midpoint of this and that, you get this point F. And the claim is that the tangent at C passes through the line through E and F. This construction is a lot like how we got C, right? To get C, we took a midpoint of this, and we took a midpoint of that, and then we took a midpoint of that. So, a couple of midpoints. So same kinds of things happening. And I think the picture is quite pleasant. You might, enjoy testing this out. You can easily construct something like this yourself. But there's one even perhaps more remarkable fact about this tangent here. Remember, in the parabolic case, this tangent was parallel to the base. Okay, here it meets the base P0, P3 at a certain point H. Okay, so to illustrate that, I've moved the control points around a little bit. That's easy to do in this case. If I just slide the control points along these vertical lines on which they're sitting, then they'll still have the Archimedean property because I haven't changed the equally spaced lines. So that's what I've done. I've moved P1 down here, and now our polygon is a little bit non-convex, but that's all right. And so now the curve has a more obvious cubic aspect. Okay, there's the base down there. And here is this tangent at C, and they meet at this point H. And lo and behold, H is a point which is also on the curve. So that's, I think, very, very pleasant. And I think it's giving us a sense that there's really a lot of things to explore here with both these Archimedean cubics and possible extensions of the things that we're doing. I mean, a natural question is, to what extent is what we're doing now generalizable to more general cubics? That's a very natural question. The Archimedean result is not going to hold as it's stated, but we may look for some variant or generalization which holds in that larger picture. So I don't know what the answer to that is. Maybe one of you can figure it out. Another very obvious natural generalization or extension is what happens if we move from cubics to, say, quartics? Can we identify a sort of a special family of Archimedean quartics for which we get an area formula of the Archimedean type? And if so, is there still a constant 4/3 involved? And what happens there? Again, that's something that I think we're going to have a lot of fun exploring. And while I have this picture here, I would like to point out that this looks like a usual cubic function, doesn't it? A function of the form y equals f of x, where f is a cubic polynomial in x, like y equals 2 minus x plus 3x squared plus x cubed. Okay, sort of that up and down shape. And those are examples of Archimedean cubics. So in particular, even y equals x cubed falls into the family of cubics that we're talking about. And in particular, if you want to find the area of a slice of y equals x cubed, or in fact any other cubic polynomial, you can use this version of Archimedes' area formula. You just draw the secant, find that inscribed triangle that we need, and you may have to think a little bit about how to do that, and then you just take 4/3 the area of that appropriate triangle. This is definitely something that should be appearing on calculus courses around the world. All right, so this is very exciting, and we're going to be looking, of course, at a proof of this. So we're going to go through this in general and derive formulas for a lot of things, which will allow us to make further investigations. And we're going to establish this area formula in complete generality, not just when the parallel lines are vertically arranged like they are here, but in complete generality using the algebraic calculus framework. And if you've been watching the last few videos carefully, you'll actually be in a position to do that yourself. I've already told you all the ingredients, more or less. You'll be able to verify that yourself if you spend a few hours doing it. Now, this opens up this whole big world of sort of algebraic geometry, but looking at it from an analytic geometry point of view, maybe almost like a 17th, 18th, or 19th century point of view again. And I think we're going to have an opportunity to explore a lot of additional features, some of them coming from differential geometry. Okay, in particular, I'm thinking of curvature, which is really interesting. The Frenet-Serre frames and formulas, etc. And I'm also thinking about algebraic geometry. So sort of 19th century things like the group structure on a cubic. That's a really interesting algebraic aspect of a cubic curve, even one like this. Even one of these de Castiglione curves will have a group structure. In fact, we'll have occasion to look at that group structure from a different point of view. I'll tell you about pods and how that's a very interesting alternative framework to understand that algebraic structure. And we'll also be looking at polarities, generalized polarities that ultimately will give us, I think, a much bigger and a broader picture about what a curve actually fundamentally is. Okay, and that will have all kinds of ramifications. But the starting point is we're going to look carefully at the Castiglione-Bézier curves, where we can get our hands on everything. We can make computations, we can write everything down, and we can see things in all their beauty. So I do hope that you'll join me for the rest of this exciting course.